Here is an orange. Its volume is about 4.19. Now, imagine an orange, not in 3 dimensions, but in 1000. What would its volume be? You might expect something enormous. After all, more dimensions should mean more space. But the answer is the opposite. In 1000 dimensions, its volume is almost zero. An orange is almost empty. Here's why. Let's start with something familiar. The area of a circle, the volume of a sphere. These formulas seem like completely different ones. But actually, they're the same pattern, appearing in different dimensions. In fact, the volume of an n-dimensional sphere of radius r is this. Set n equals 2 and n equals 3. You obtain the area of a circle and the volume of a sphere. Here, gamma is the gamma function, or natural extension of the factorial. We don't need to understand it fully now. Let's fix the radius at 1 and calculate the volume in each dimension. In dimension 1, n equals 1. Dimension 2, n equals 2. Dimension 3, dimension 4, dimension 5. So far, everything feels normal. As dimension increases, the volume increases too. But now, something strange happens. Let's go further, all the way to dimension 1000. Now, watch what happens. The maximum occurs at dimension 5. From dimension 6 onward, the volume decreases. After that, the collapse begins. This is not what we expected. By dimension 1000, the volume has almost vanished. But it's not zero. I can't believe this result. Can you? Why does this happen? Look again at the formula. As n grows, the gamma function in the denominator grows far faster than pi in the numerator. The denominator explodes. The fraction collapses. The volume shrinks rapidly towards zero. So where did the volume go? It didn't disappear. It moved somewhere. In high dimensions, almost all the volume of a sphere concentrates in a thin shell near its boundary. The interior becomes almost empty. This is not just intuition. We can prove it mathematically. Consider an n-dimensional sphere with radius r. The volume of this sphere can be written like this. The volume is proportional to r to the power n, where Cn is a constant that depends only on the dimension. Let's focus on a thin shell near the boundary. Suppose the thickness of this shell is AR, where A is a number between 0 and 1. The larger A is, the thicker the shell becomes. If we remove this outer shell, the radius of the remaining inner sphere becomes r minus AR. Therefore, the volume of this inner sphere is this. Now, we compute the ratio between the volume of the inner sphere and the volume of the whole sphere. This simplifies to 1 minus a to the power n. This quantity is raised to the power n. Since a is between 0 and 1, 1 minus a is also between 0 and 1. So, as n increases, this quantity goes to 0. But what did this quantity represent? It was the fraction of the sphere's volume that lies inside the shell. As n grows, this fraction shrinks toward zero, which means almost none of the volume remains inside. Instead, almost all of the volume moves toward the boundary. That's why a thousand-dimensional orange has almost no inside. This is the mathematical reality. This counterintuitive phenomenon is known as the curse of dimensionality. In high dimensions, our geometric intuition breaks down. Space behaves in ways we are never trained to imagine. And remarkably, this is exactly the kind of space where modern artificial intelligence operates. The volume of a sphere turns out to be deeply connected to artificial intelligence. That is another story.